these two can be derived from the DL. Having said that, so how do we start? Very simple things. I just want us to see how easy these things come out. And we are going to say the first strength we are going to deal with is, we are saying DL is going to be equals to, remember we express dimensions of cylindrical in terms of AR, A, phi, cap, and AZ cap. That is how we express them. And so we just find out if we had as an elemental length from point R to Q, how would you express this length, this elemental length? You can see that we say that the length of this, or the radius of the cylinder, is expressed as, oh, sorry for this. This is not AR. This is supposed to be A rho. So this is how we express the length. We are saying that the radius of the cylinder is rho. Therefore, the elemental length between R to Q is going to be D rho, because it is a small length of the radius. So we call it D rho, and that is sufficient. So we are saying that we are going to introduce D rho there, so that we are saying that that small length from R to Q is rho. Then we want to find, I'm going to keep on rubbing this one so that we see where we are. Then the other length is from point, which is a curve, from point Q to point B. It's actually a curve, like part of the circumference. Remember that this is the circumference of the cylinder, and therefore QB is actually part of the circumference. And if we express circumference to be, give it what? Which symbol are we going to use? Circumference. Give it a funny symbol, like, I don't know, circumference, DC. Circumference is equals to C. So if you wanted to find the length QB, it is simply a fraction of the circumference. And if you remember, we say that here, the angle, we normally find the angle, the length of an arc. I want you to remember this. Length of an arc. We normally say, which is part of the circumference, we normally say is equals to the differential or the radius, okay, the angle subtended by the arc, which is d phi. So you can see the entire angle is phi, but the small angle subtended by the arc QB is simply d phi. So what we do, we normally say that the angle subtended by d phi divided by 360. Remember what we used to do in primary school? Divided by 360, then multiply by the circumference C. That is how we used to find the length of the arc. So how do we do that? Technos part 2, rename yourself and make sure that you include the registration number, and you don't share the video. Technos part 2, you know what I said. So that is how we express the length of an arc. And we are asking ourselves, the circumference is obtained by 2 pi radius. Remember, that is how we find the circumference of a circle. So now that we know this, and we are saying that this 360 is equals to 2 pi. That is simply in radians. So we normally say that this goes to d phi over 2 pi times 2 pi rho. So we are saying that the elemental length d phi, which is in the direction of d phi, is going, no, you can't express that. The elemental length QB is going to be given by, cancel that, is going to be given by rho d phi. It is in the direction of a phi. So that is how we obtain, that length, this length here, rho phi. So this is what I was trying to derive by showing you how we are getting that. So it is simply rho d phi. That's something you must remember. That's something you must always endeavor to remember how that comes about. Remember, we have started with the length of the arc, and we know the length of how it finds the circumference of the circle, and then the arc is substituted by angle phi, and therefore the length of that arc is going to be given by rho d phi, and therefore that elemental length in the direction of a phi, now we include it here, d phi. So that is the length, the elemental length in the direction of a phi. And of course, the other one is simply dz. You don't even have to think. You said spherical coordinates and rectangular coordinates, the z direction remains the same. So my elemental length becomes rho or d rho a rho plus rho d phi a phi plus dz az. So that is where we are. That is the most important thing to remember. You must endeavor to make sure that you don't get lost at that point, because if you do, you will be in trouble for you to progress forward. So I'm lapping this now. So we have derived the elemental length in the cylindrical coordinate system. So once we have done that, so I think we should now be able to move to the elemental surface area in cylindrical coordinate system. So what we have just done is deriving this. So this is where I jumped. So I have just tried my best explaining the concept regarding deriving the elemental length. So what we now jump is to develop the elemental surface area from a cylinder point of view. And if we just follow the same idea, now that we want to find this service, now remember we want to find this service. Like the one service is this one. Oh, if I can write it black, you not see anything. Getting notifications here that are not making me happy. Let me focus. Priority only. Okay, there are some notifications that we're getting. So here the idea now that I want now to work with is that this is going to be my elemental surface area. This is now going to be my elemental surface area, and I'm calling it A, B, Q, C, the one I've shaded in black. So if you had that elemental surface area and you wanted to find its dimension, okay, its value in terms of vectors, you'd simply say the area AB times length AB times length QB. Then you say that the vector is going to be facing outward from the volume, and that is going to be A rho. This is what we have said. So once you know that, we can then say that we have found that this length of that arc is equals to rho d phi. And then going up is dz. So we simply say dz a rho. And this becomes the first elemental area along the direction a rho. If you wanted to find the elemental area which is represented by SRQC, this on this side, you would simply say this small length between R to Q, or length RQ times length what? Length DZ or QC, which is equals to RQ we have found to be DR, not DR, D raw is D raw times QC, which is DZ, and then the direction is going to be outward from the volume, which in this case is opposite of phi, of d phi. Remember, phi is going in this direction. Therefore, we say that is outward, therefore becomes negative a phi. So we can say that this, we just introduce negative a phi at that point. So that is how we would develop the elemental service areas. And so what we are simply saying, dz, oh, dz, 0 dz, confirm that, 0 dz phi. So what we are saying, therefore, is that the one that would be on this side would simply represent this, except that it do not have the plus. So we, for the initial one, we do not introduce the negatives. That is why we have developed this one with you. We have also developed this one, and of course, you can also be able to show that the one that is facing in the Z direction is going to be represented by that last one. Sharon, you don't want to say you? We said that we are not going to be having any video for anybody, including me. That's why I'm switching off your video. All right, so I think that is clear. That is how we do the elemental volumes. Notice that the only difference that we are having between cylindrical and rectangular is that we are having a new element, rho, plugged in at some point because of the idea of the length of the arc. The length of the arc is the one that introduces that rho. So it is important that you see that is the only difference. Otherwise, there is not much difference. So we have done this, and I don't think there is any cause of alarm regarding how we have derived that. Sorry, I believe you can already. Let me see if it will work. Yeah, it had refused to lab. So I was trying to lab there. So now we are doing this last subsection, and the volume is simply the way we did. We just multiply all the dimensions, and we just come back here. Where is it? Just come back here, and I want to lab these ones again. And if you wanted to find the elemental volume that is shaded, you would simply multiply all the dimensions, and all you need to remember is each dimension, this one, and where is the, yeah, and this one. So you simply say the volume dV is equals to rho, d rho, d phi, and dz. And remember, this one is a scalar. It doesn't have any direction. So you don't include some funny things there. Dina is telling me to repeat on the difference between rectangular and cylindrical. We are, okay, first of all, I will repeat that once I have finished with this. And we are simply saying that you just multiply the dimensions rho, I'm just bringing the rho outside. for the sake of these are the following the order. And also notice that you don't mix them up. You don't start with DZ, then 0, then 0, then D5, or in any other order. You have always to follow this order. We always start with the row comes first, then phi comes second, and Z comes third. That is the same way if you are having dV in rectangular, you'd say dx, dy, and dz. So you cannot say that you are going to have dy, dz, then dx. This one is not acceptable. This one is never acceptable. So the same way, you cannot have rho, dz, dphi, d rho. You cannot have this one either. So you always follow that order. So again, that is easy. I will very quickly ask, repeat for Dinari what we are saying about the difference between this is that when we expressed ds in rectangular, we said is equals to dx, dy. I think we started with dy, dz, ax, dx, dy. No. We followed some order like I'm telling you. So dx, dz, ay, and then we had dx, dy, az. So what we are saying is that if you observe similarity between these two, you would observe that this is following the same order, that ax is following the idea of ax, and az is following the az. And of course, d law is equivalent to dx. So the only idea we are introducing is this element that is not anywhere here. It is coming there because of the length of the arc. That is the one that introduces that concept. So that is for Dinari. Hope you understand. So you can always comment on chat that you have understood. So we have actually finished with the cylindrical coordinate system. And we are simply saying that we can split this up to show that one surface, if you split it from this volume, just hope you can see this. If you remove each of these surfaces, if you remove this one, it would give you this surface is the one that is giving you this. But now you're saying that we are considering that the one that is facing the arrow direction, so it is actually the one on this back side. Therefore, this one that is facing towards the row direction is actually this one that is facing that one. So this one is that. And the one that is going up is the one at the top here. So the one that is at the top is the one that is represented by the one I'm just splitting them up. So what we are saying is that you can be able to visualize how each of those small surfaces actually looks like. Okay, so again, another small pause for the sake of questions before we move to part C on spherical coordinate systems. We're going to be dealing with the differential length, differential surface, and differential volume. And we want to say now that in spherical, we always remember how the diagram looks like. And remember, it's always here. This is always the most important thing to remember, that how the spherical coordinate system fits in to the one that we always know, that is the rectangular or the Cartesian coordinate system. So we always know that the length of the radius is expressed as r, opposite to what you are expressing the radius of the sphere. That is something you need to remember. And number two is that this phi always remains the same for both the sphere and the cylinder. Lastly, we said that the angle theta that is now new is the second parameter of spherical. It always runs from z downwards. It runs z all the way to pi. It has the limits from 0 to pi. So that is a major difference. So you must always be able to draw that diagram of as much as possible. So we were here, and we are saying that the idea is that you should always be able to generate this diagram. Once you're able to generate this diagram, you can always be able to express your elemental length, so differential elements in any coordinate system, or now currently the coordinate system. So I want us to show you how we can get this DL without necessarily you getting mixed up. And the idea is rather simple, that that this is length, the radius r. So the elemental length from this point to this point is simply dr. When we say elemental length or differential length, we are saying that it's a small portion. You had r as a radius, so small portion of r is dr. So we are saying that simply becomes your elemental length. So it is going to be, so we are going to find dl, a vector, is going to be simply be in the direction of ar, we are going to have dr, ar, then plus in the direction of a phi, so phi is this direction, but this phi comes as the last term. So before I actually deal with that, I'll deal with the theta. Theta is the second term in the spherical coordinate system. And we are saying that you have moved, you are moving from Z towards XY plane to make the angle theta. This is where you make the angle theta. So how do we do that? I want to simply say that the first step, and this is the step that we had not done last time, and I said I would repeat it in due time, but this is the time has come, that if this is R, this is going to be the arc of a circle, of that circle. And that arc of that circle is simply a portion of the full circumference. So we are simply going to say is going to be given by d phi over 2 pi, which is 360, times 2 pi r. So if you cancel this and this, you are left with that arc at the xy plane is going to be r d phi. But then when you move it towards the z direction by an angle, okay, of course, from z towards xy plane, it is going to diminish in length. And I want to show you that, and that is the part that we had some trouble last time or last week. You can see that consider this to be a sphere, and similar to the Earth, we can say that the distance between two longitudes at the equator is actually bigger than at some latitude towards probably 30 degrees or 60 degrees towards 90. So remember that we are measuring this angle from Z. So we are saying that when theta is equal to 90, the arc is actually full length, is equals to r d phi. So this is going to give us 1. So what I'm actually saying is that at 90 degrees, the arc is full length. But as you move up to make some angle different from 90, then the length of this arc will become smaller and smaller. You can see that one is smaller than that, that one is smaller than that. And when you are almost near the North Pole, the length of that arc becomes smaller and smaller, it becomes 0. And that characteristic is defined by sine of 90 degrees. So we are actually multiplying our length of the arc with sine theta. So that is the only difference that you're going to realize, that the length of this arc is a function of theta, and therefore we are saying that this length of this arc is going to be given by, I think I have written so many things, so I won't write it here again. It's going to be given by sine theta, and what we have found out here, r d phi. So that becomes the dimension of this arc as you move along towards, the North Pole, or from the North Pole downwards to the equator. So having said that, so I think I will have my board because it's again getting cluttered. So that is the small item that I had